Hi, today we're going to go over the Machine Learning Coursera course Practice Lab Neural Networks for Handwritten Digit Recognition Binary. We're going to use a neural network to recognize the handwritten digits 0 and 1. First, we're going to run our packages Numpy, Matplotlib, TensorFlow, and some grading packages. We're going to load our dataset into X and Y, then view our variables. The first element of X looks like this, and the first and last element of Y looks like that. The dimensions of our variables look like this, and they look correct because we have 1000 training examples. Visualizing the data. So these are our first 64 digits. Model representation. So now we're going to use TensorFlow to code our machine learning model out. And I really like this image because it tells us what the model is doing simply. So we have 3 dense layers with sigmoid activations. So the first layer has 25 units, the second 15, and the third 1. Now we're going to use the Keras sequential model and a dense layer and dense layers with sigmoid activations to construct the model network above. So the code looks like this. We have 3 dense layers. And they're going to each have 2 parameters. The first one is going to be the number of units in the layer. And the second is going to tell us the activation. In this example, it's going to be sigmoid. And 15 sigmoid. Last one has 1 layer, 1 unit. So this is a summary, and the test says that's all passed. Next, we're going to see the number of parameters, and we're going to see the weights. And so this doesn't really mean anything to us because we're not as smart as the computer. But now we're going to compile it. We're going to fit our model. So this sounds really complicated, but let me try to explain it simply. So we know that a loss function tells us the difference between predicted and actual values in a mathematical way. And so in this case, they're using the binary cross entropy loss function, which tells us some difference between the predicted and actual values. And then remember that we were using the gradient descent algorithm to try to minimize our cost or our loss function. And so in this example, again, we're going to use the gradient descent algorithm. And so the Atom optimizer is using the stochastic gradient descent algorithm to try to minimize our losses, which is going to help us find really optimal parameter weights and fit our model really well. And so the alpha learning rate is going to be 0.001 in this example. So we're going to fit our model, and we're going to have 20 epochs or 20 passes through the model. And we can see that it's working because our loss is decreasing. Next, we're going to run predictions. And so Keras predict is an array, and the output is interpreted as a probability. So, for example, the first one is saying that, so in this example, the input is a 0. The model predicts the probability that the input is a 1 is nearly 0. So it's saying that there's a 3.951% chance that the input is a 1. And the second example, it's saying that there's a 98.5% chance that the input is a 1. And so how do we determine it? Well, in this case, we're going to use a simple if-else statement. So if it's above 0.5, then we're going to say it predicted a 1. Else, we predicted a 0. And now we're going to run it for 64 digits. And we can see that predicted and actual values match pretty well. So now we're done with that part. Now in this next section, we're going to go over a Numpy model implementation of a dense layer with Numpy using the forward propagation algorithm. And we can utilize it to build a multi-layer neural network. So it's asking us to calculate one of these dense layers. So here are the instructions. We're using a for loop to visit each unit j in the layer. So we're going to visit, well, the code is right here, but I'm going to try to explain it. So there's a for loop that visits each unit j in the layer. So we're going to calculate for A1, then A2, then A3, and then we're going to perform the dot product of the weights for that unit. So dot product between W and X, and then we're going to sum the bias for the unit B bracket J to form Z. So sum the B's afterwards to form Z. And then we're going to put an activation, so Z is like WXB. An activation function GZ is then applied to that result, so G of Z. So let's code it out. Z is the dot product between W for that specific column and AN plus B bracket J, and there's going to be a for loop here for J and range of number of units. A out is going to be G of Z. And it worked. So we're going to build the 3-layer neural network using the dense layer that we wrote above and copying the weights and biases from above. And we're going to make predictions on it. And we can see that worked pretty well. Now we're going to go over the optional sections using vectorized Numpy model implementations. So vectorization, so these vector and matrix operations can speed up the calculations. In this specific example, it's saying that we're going to map mul or matrix multiply between x.t, which is the transpose of matrix X. Transpose just means that we flip the rows and columns, and W plus B, and applying the sigmoid function on it, and this is the shape of it. Okay, now it's asking us to construct a dense layer. So we're using A, N, W, B, and G, and it's going to be from this slide. So we want matrix multiply between A, N, and W. So A, N, or our X, is going to be multiplied by W and then added with B to form Z. And then we're going to use the sigmoid activation function to apply it on Z, so G of Z, to form A out. And so that's the plan. So Z is going to be equal to np.mapmul between AN and the W added with B, and A out is going to be equal to the sigmoid function applied on Z. And it worked. So we're going to utilize it again to make predictions. And this is showing us what one of the misclassified images looks like. And we're done with the lab. And this tutorial is telling us how broadcasting works. And broadcasting is helping us to speed up our matrix vector operations. And thanks for watching.